Last time we talked about some general conditions for convergence to an invariant subspace, a linear invariant set. And we said these conditions could be used to show that if you have such subspace, which could correspond, for instance, to a synchronization pattern between dynamic systems of different dynamics, of different dimensions, and so on, then it allowed you to show that indeed the entire behavior of the system always converged exponentially to that pattern. And then, of course, if you applied this in a feedback context, then you could choose a control law to make sure that you converge to a particular pattern or you switch to a particular other pattern and so on according to the context. So then we moved to a few extensions. We talked about the discrete time case. So remember we said that if we have a discrete time nonlinear system, we can still look at a virtual displacement because these virtual displacement, this differential displacement are done at fixed time. Okay. So we can still look at that, and it will have the usual form df over dxi times delta xi. And we can still, if we want, also transform these virtual displacements. So for instance, we could have theta of xi and I delta xi, which would be the differential transformation. So we said that if instead of computing d over dt of delta x transpose delta x, what we're going to compute is delta xi plus 1 as a function of delta xi. Delta xi plus 1 squared is a function of delta xi. And of course, that's simply going to be delta xi df over dx transpose df over dx I dxi. And if we want this to be decreasing, then it will mean that it has to be less. So we know that this is always less than sigma I square delta xi transpose delta xi, where sigma I square is the largest is the largest eigenvalue of this quantity. So this eigenvalue, of course, is positive, right? So that's why I wrote it as sigma I square. And if we want this to be shrinking, so delta x transpose delta x decreases if this sigma I is, which is a positive quantity, right? Sigma I square is less than 1. So we can do this directly on delta x, or we can do it on delta z, delta z. And if we do it on delta z, what we find is that instead of the Jacobian, here we have, of course, some kind of generalized Jacobian, discrete generalized Jacobian. And this will be less than some sigma I square. So maybe to be consistent, let me call this sigma I square of df over dxi, right, times delta xi transpose delta x. And so this will be less than the largest eigenvalue of this matrix, which is the largest singular value of the matrix Fi. So sigma I square of Fi, right, delta zi, delta zi. And of course, delta z transpose delta z will decrease if this sigma I, right, is less than 1. Now, we said we could now look at hybrid systems. specific case, as a particular case of hybrid system, particularly simple case of hybrid systems, composed of a sequence of a continuous dynamics and a discrete dynamics, as you would do, for instance, if you had to design an observer for a continuous physical system using discrete measurements. Okay. And so then we saw that we had two terms to consider. The first had to do with the contraction or expansion rate of the continuous part. So if the continuous part was contracting, lambda was positive. If it wasn't, lambda was not, right? Multiply by the corresponding sigma I. Okay. And this had to be less than 1 if we wanted to the sequence of two systems, one perhaps contracting, perhaps expanding, the other one perhaps contracting, perhaps expanding. But if we want the sequence of the two to be contracting, then we want this product to be less than 1, which in term, for instance, allowed to have questions like, suppose I'm trying to build an observer for an unstable system, so have actually an expansion rate. This lambda is negative, minus lambda is positive. So this term then keeps increasing exponentially. Then hopefully, of course, in my observer design, I get a sigma I, which is frankly less than 1. And it tells me then, how often should I sample the system and apply this observer to get an overall stable behavior. Okay. So that was the general idea. And most of these results, of course, that we derive can also be stated in the discrete case. So we had started doing a little but very practical application, which was the strap-down navigation problem, which is a standard question where you have a position, a rigid body which has a position r and an orientation described by some vector x. And you have continuous measurements of angular rate omega and inertial acceleration gamma. And these measurements are done in, on the rigid body. Hence this term of strap down, which comes from aircraft design. And so the question is then we have these position and orientation are measured at discrete times. And we'd like to build an observer. So something which gives us an information all the time, an estimate of all the time, okay, for x, r, and the velocity r dot. So we said the dynamics of the system is composed of 3 stages, okay? One is really a kinematic relation which relates the derivative of the orientation vector, so for instance, a set of Euler angles, to the angular rate. Okay. And here you have this matrix, which is some kind of some kind of Jacobian, which relates this angular rate and as a function of the orientation, derivative of orientation. Then v dot, the acceleration, is equal to, so r dot is v, right? So v dot, the acceleration, is equal to some transformation matrix, which also depends on orientation, so just the coordinate change, right, times the measured gamma, right? And of course, omega and gamma are just measured functions of time, right? And of course, just the definition of v, which is r dot equal v, which gives us a third equation. So we could do this directly here. What we're going to do is something a slight modification of this, which is we're going to represent orientation using quaternions rather than, let's say, Euler angles. One of the reasons is that this is something which is very commonly done to avoid singularities of representation of orientation. And the other reason, even more obvious from our point of view, is that the analysis becomes even simpler, actually, using the quaternions. Okay. So if you do use quaternions, then we still have, of course, r dot equal v. And then we have a quaternion vector. I'll come back to that in a second. And the kinematic equation then become q dot equal 1/2 of omega q. I'll explain that in a second. And then v dot is still a transformation matrix A, right? In a sense, the same one, but now it's computed based on this quaternion vector q and then gamma of t. And just to be consistent, let's call this omega of t. So let me explain this, right? So quaternion, as you probably know, right? So the idea is that one of the ways of saying this is that to avoid these singularities in representation of orientation, instead of using a three-dimensional vector, three numbers to represent orientation, you're going to use four numbers. Okay? And so you get this quaternion vector, which is cosine of theta over 2, and n times sine theta over 2. So it's composed of these two components, cosine over 2 and n, well, these four components, cosine over 2 and n sine theta over 2, right? Where n is the unit vector around which the rotation happens, okay? And theta is the angle of that rotation, okay? So in other words, you represent orientation, right? Which means you know where you are with respect to some coordinate system. So in terms of a rotation, okay? And so that rotation, you could give a full matrix, but that, of course, that would be too redundant. So what you say, well, rotation can be entirely defined by the axis of rotation, and the unit vector along this axis is n, okay? And once you have this axis of rotation, then you just need, of course, the angle of rotation around that axis. Okay? So quaternion representation is a four-dimensional representation of orientation instead of just, let's say, three angles. And then the kinematic relation, omega, so let me write it here. So now we have this omega, which of course is a function of time, which plays the role of this, right? But now it's a matrix. And it's based, of course, precisely on these. Maybe I'll pick another color which will be more visible. So let's see. this. So you have this measured angular rate omega, which has three components, omega 1, omega 2, and omega 3. So what you build is a matrix, which is this matrix. And so this is kind of similar to a cross product, right? And this, this matrix here is the one you put in here. Okay. So, as far as the system itself is concerned, what can we say, okay, about this system? In terms of, so this is a continuous system. We're not talking about anything discrete yet, right? We're saying that the physical system here, what can we say about it? Well, first of all, as we noticed last time, right, you have a hierarchy, right? So basically, you have a direction of information flow, right? You have Q dot is equal to this. V dot is a function of Q and this external function of time, okay? And then R dot is equal to V. Okay, so you have this hierarchical structure. Okay, the flow of information is in this direction, which of course directly reflects the physics of the system. Okay. And what can we say about the elements of this hierarchy? Well, so this, let's just take this one, R dot equal V, right? So R dot equal V, is that contracting? No, it's just an integrator, right? So it's just indifferent, right? So it's not contracting, it's not expanding, right? It's a linear system with a pole at 0, right? So in an identity metric, it's just indifferent. Okay, so what about this term? Well, this term, as far as this term is concerned, right, Q is something coming from above, right? So it's also a function of time, right? And gamma is a function of time. So it's, again, an integrator, right? So again, something which is indifferent. Okay. Now, what about the first one? What are its contraction property, in at least in some obvious identity metric? Remember when we said this, right? Incidentally, we said, of course, this computation has to be done in the same metric, in the same theta for the continuous and the discrete. Okay, but so getting back to just the continuous physical system, what can we say about this first equation? What's the Jacobian of this system? Yeah, the Jacobian of the system is 1/2 of omega t, right? Right? This is a function of time, right? So Jacobian is just this one, 1/2 of omega t. And what is omega t is this matrix, which corresponds to this vector product, right? So cross product. And so this matrix is obviously skew symmetric. Okay? So what we have, therefore, is a hierarchy of 3 systems. It's very much like just a sequence of 3 integrators. Right? We have a skew-symmetric system, so it's indifferent. Okay, it's neither contracting nor expanding, right? We have this system, which is just an integrator multiplied by, time-varying things, right? And similarly, we have this system, which is just an integrator. Okay. So you see that, for instance, if we were measuring orientation, velocity, and position at each time, then it would actually be very easy to build an observer, right? Because what would we have to do? Well, we would copy the system in between measurements. So let's say we take the last one, for instance, okay? Suppose we just take this one. Very easy to build an observer, right? We just copy the system, and then we add discrete updates, right? And what should the discrete update verify? We should verify this equation, but since the system is indifferent, lambda is 0. So it should just mean that sigma I should be less than 1, right? So you have a sequence of 3 independent systems, right? If we were measuring discrete orientation, velocity, and position, we would just have to make sure that the discrete update of our estimates is discretely contracting, because as far as the continuous part is concerned, it's indifferent. Okay. So that, for instance, that's what we can do for, let's say, the first term. Okay. Now, the only subtlety here, but in a sense that's just a matter of finding an equation that fits. The only subtlety here is that we don't measure position, velocity, and orientation. In some instances, people do, right? Here we assume we just measure position and orientation. We don't directly measure velocity, so we'll have to do something a little more subtle for velocity. Okay? But if we were measuring position, velocity, and orientation, then it would be very easy what to do. All right, so what do we do? Well, for the continuous part, so let's pick the first equation, right? We have a hierarchical system. We can build a hierarchical observer, which basically just follows the dynamics of the system, follows the physics of the system, right? So if we build a hierarchical observer, it means we're going to have q hat dot, with hat being, of course, the estimate generated by the observer, is equal to 1/2 of omega q hat. That's the continuous part. Okay. And then a discrete update part, which would be q dot I plus, q I plus hat. So update of the estimate at time I just after the measurement, okay, standard notation, plus being your update just after the measurement, okay. And of course, we can take some kind of local generalized Jacobian here, actually local Jacobian because we pick an identity metric, q hat I minus plus I minus f1I q I hat. Sorry, qi, the measurement. Right. So here we have this system, right? So we have an identity metric. This is just an external term, right? And the Jacobian of this system is this, okay? And we want sigma of f1i, right, to be less than 1, right? Because the term for the continuous part will give us e to the minus 0t, delta t, so that will be 1. So the only term we care about is sigma I. Okay. So for instance, you could just pick, a scalar alpha, right, and 1 minus alpha, and then, of course, you would want this alpha to be less than 1, right? Perhaps you want to do something more complicated for noise reasons, right? But just if we didn't worry about noise, we could just pick a scalar, right? Just a scalar gain instead of a whole matrix, right? And the scalar gain would be less than 1, which would certainly satisfy this. Okay? So for instance, okay, with alpha between 0 and 1. Okay. Yeah.
QI plus 1 or
Oh, sorry. All right. So let me explain. This is a standard notation, but that's fine, I guess. So, so when we say Q hat I plus, okay. So I, of course, is the time instant. This, of course, means estimate, right? And this means once we have the measurement, okay? Once we have the measurement, we update our estimate of Qi. And we update based on Qi minus, which was our best guess, our estimate just before the measurement, and the measurement. And of course, our best guess just before the measurement comes from this. It's the result of our continuous simulation all the way up to just before the measurement. Right? So this here, but yeah, good question to clarify this. This here is going to define this.
Okay. The reason we're having an observer here is that we're assuming that the measurement is noisy, so we want to...
We could assume that the measurement is noisy, but also we want an estimate all the time. Right? The measurements are discrete time. And we want to keep generating an estimate between measurements. Right? And so that's what will do this. Okay.
Does that mean that this is a continuous function in the second one?
Which one? This one?
The second one, the one above it. Yeah, is that a
No,
continuous?
no. So okay. So think of just think of a Kalman filter in a linear system. Okay, so you have a system, an aircraft, whatever. It's a dynamic system. It's a physical system. It's continuous, right? And then you have measurements, and measurements are discrete. They don't all have to be, for instance, gamma and omega are continuous, right? But you have discrete measurements, discrete time measurements. And you're trying to do your best to have an estimate of where you are all the time, okay? So instead of an aircraft, you could think of a submarine, right? Or an autonomous underwater vehicle, right? So it goes down, it does its thing, perhaps, taking measurements on the mid-ocean ridge or whatever. And from time to time, it comes back and waves to a satellite, asking, where am I, okay? And so, when it was underwater, it was doing whatever it could to figure out where it was, right? And then from time to time, it gets this precise measurement, okay? And then it updates everything, okay? So in that case, of course, you have the measurement is so precise that in a sense you throw away all you thought before, right? You don't really mix things up, okay? Because the measurement is very precise and very infrequent, okay? But in most cases, you really mix up your best estimate and the discrete measurements because all of them are corrupted by noise, and you're trying to do the best possible trade-off between your estimate coming from the simulation and your measurement. Okay? This is a very standard structure. You find it in in AI terms. This would be called a predictor-corrector system, right? Where you have prediction between measurements and then corrections when you have the measurement. Okay. So, and the point of all of this is that you can do this in a completely nonlinear context as well. But yeah, good question. Any other question? Okay. So this was for the first one, okay? So now, of course, we can do exactly the same thing for the last one. The last one is even simpler in a sense because it's linear anyway. But we can do R hat. So if you want, this is between measurements. And this is at measurement. Okay, so it's called measurement incorporation. So incorporation of the discrete measurement. So you can do the same thing here, right? Between measurements, you do R hat dot equal V hat, right? Because that's the best you can do. There's no new information coming, right? So you just use your model of the system, which is in this case is R dot equal V, right? There's no new information coming. And of course, at measurement update, you're going to have an equation very similar. R hat plus I is equal to F3 sub I R hat I minus plus identity minus F3I Ri. Okay, where this is again the measurement. Okay. So that's for the third term. So you can do the same. And of course, similarly, you want with sigma of F3i less than 1. Okay, and you see, of course, you could pick this actually all the way equal to 0, just pick the measurement itself, but then you would not, in this update, use any previous information you may have, okay? So if the measurement is noisy, then you're not exploiting what you may have learned before. Okay. Now, for the middle one, so this would require a little calculation. But so, of course, for the between part, you just, again, simulate the system. Sorry, it's Q hat. You again simulate the system. And that, then you need a way for the measurement to update. So there's several ways to do this. Okay, this is one which is easy to both compute and implement, but there's other ones possible. Okay, and for those of you interested, I'll let you verify this works. Yeah, I'm not, maybe just to be consistent, let me just write it as the I, Ti minus 1, delta Ti minus 1 of Ri minus Ri minus 1. So what is this? Okay, it's saying between measurement you do this, okay, and for the update you do this, okay. So the new estimate is equal to the old estimate plus these two terms, okay. So one is basically just, if you want, a coarse velocity estimate, right? Which just says, I have 1 over delta Ti, and I'm just going to look at the difference of position at now and at the time instant before, okay, divided by the time between the measurements. So that's as basic as it gets, right? And then you correct this term with this, okay, 1 over delta I times the integral between the same two instants, the previous measurement and now, of v hat generated by this model. Okay. So in other words, here, this feeds two terms. Okay, it feeds this terms, and it also feeds this term. Okay, and let you verify it's just a few lines of calculation, but this indeed verifies the contraction condition. And so therefore, you have now an observer for this system, okay, which is a hierarchy which follows the information flow in the real physical system, follows the physics of the system. And you have, therefore, a hierarchy of contracting system, which, of course, is contracting, okay? And therefore, the entire observer is contracting, right? Now, of course, by construction, it was also made sure that the real system is a particular solution of the observer, right? That's true for the first equation, and it's true for the second equation, although it's more complicated. It's also true for the first equation. Second equation, right? Because if you have the real system, then these two terms are going to cancel. And of course, it's true for the third equation as well. All right? So you have this observer, which is contracting because it's a hierarchy of three contracting systems. Each of these contracting systems is itself a mixture of a continuous system and a discrete update. And the observer, of course, has been chosen so that the real thing is a particular solution of the observer, so that the observer is contracting to the real thing, okay, to the real state, okay? So in a sense, here we have a mixture of a few simple ideas, right? The fact that hierarchy of contracting system is contracting. Each of these subsystems is itself a composition of a continuous and a discrete system which is contracting. And then you can put all of those together. Okay, questions about that? Okay, so it's just a simple example. I mean, you can get much more elaborate ones, but yeah.
In practice, how can we implement the continuous part? Shouldn't we just, again, have some sort of...
Okay, so, yeah, okay, so depends on the problem, but typically it's going to be done on a computer, right? So it says the computer runs a simulation of the system, right? Now, perhaps you can build another physical system which can run the simulation continuously, but typically you're just going to do it on the computer, right? Don't forget here that you have the measurements, discrete measurements, which are limited by the physics of the sensors, right? Or the physics of what you can do. At the extreme, this example I was giving with the underwater vehicle, which has to go and see a satellite, right? Most of the time it's underwater, so it doesn't talk to the satellite. Okay, so it's linked to the physics of how often you can have the measurements. And then you have your computer, and you assume your computer can do a good job at simulating continuous dynamics. Okay. Computer is comparatively much faster than the measurements. Yes?
So I guess I had a question with this strategy. It seemed to work really well when you're doing stuff which is integrating. but you're going to have all these discontinuities, and if you were interested in something which was the derivative of your estimate, won't you have discontinuities in your observer?
The derivative of your estimate. Well, we do that for v dot, right? We do that for v, which is a derivative of r, right? But we do that starting from a system of state equations, right? So you know, it's a typical problem of having something and you want its derivative, right? But for this, you need the equation for the derivative. The differential equation defines the derivative, right? That's what we did in our very, very first example when we had this van der Pol system, right? We had a second-order equation for the van der Pol, right? And we had, and then we computed the derivative based on the measurement of position. Right? So that's part of what you often do for observers. You compute derivatives, right? But you need a model, right? And a model of how the derivative changes. Okay. Other questions about that? All right. So now, one of the reasons to pick non-trivial f's up there, just not alpha and so on, could be noise, okay? And we won't do this in detail here, but you can do kind of a stochastic version of these contraction ideas, at least to some extent. But we'll see or state one application of that, the stochastic contraction. Back to our quorum sensing idea, okay? The fact that you could synchronize systems by coupling them all to all, and this coupling could be done for a common variable and feeding it back to everybody else. Okay? So let's pick again this little quorum sensing system. Let's just pick scalars because it's easier, but this would work with vectors as well. So we started with systems like this, and we made the remark a few lectures ago that, you know, the same system was first equal to the sum for all j's of this, because when I equal j, this term is just 0, and that in turn this sum could be computed by just some local term minus k times nxi, and then some common term k sum of the xj's. Okay? So that's what we did the very first lecture on contraction, you know, to introduce you to this idea of a virtual system. Now, suppose that to this system, which is itself equivalent to computing a common variable and feeding it back to everything else, right? Suppose we add noise, okay? So this is a little casual way of doing it. You know, the correct way would be to write dxi is equal to something plus w times dt, where you know, you have a noise process. But let's do it a little more casually this way. You get the one-to-one mapping to these equations. You know, just have to write it more cleanly. So you have this, and then you have noise. Okay, and let's assume that actually the noise on the system is independent noise. Okay, so the noise you have on this system here is independent of the one on another system, is zero mean, and has variance sigma squared. Just to simplify, okay, all of these things can be extended. We're taking scalars, we're taking same variance and so on, but all these could be expanded just to get the idea. Okay. Incidentally, if this noise was not zero mean, that would not be a big deal, right? Because if it means that you would just add the mean, right, and then the rest would be zero mean. Right, so that's not right. And by the way, adding the mean would still preserve the fact that they synchronize, right? Except, of course, what they synchronize to would be dependent on this mean, right? See, for the virtual system and so on, you would just add the mean, right? So it's not a big deal. Okay. So now it's two versions of 2 points of views on this, okay? But let me kind of give you one. Very often in neuroscience, in biology, in statistics even, when you do measurements on social networks or whatever, you take measurements, okay, and you average them out. You take the mean of these measurements, okay? And so you do this when you, let's say, interpret, brain signals using different kinds of technologies. And you do that on groups of cells, and you do this, okay? So you take measurements, you measure things, electrical activity or other, okay? And you average it on a number of cells, right? And the motivation, typically, is twofold. One is that the sensor is itself averaging it, because you can't measure a thing on one cell, you're really measuring a spatial thing, okay, well, on many cells, okay? So that depends on the technology, but let's say in fMRI, you're not measuring one neuron at a time, okay? You're measuring lots of neurons together. And the other motivation, which is often given, is, because you're measuring all these cells, you're getting rid of the noise. Okay. Now, this, as we'll see in a second, is a completely flawed reasoning. Okay, that's what we'll see. We'll see. It's very easy to see in simulation. It's completely flawed reasoning, but let's see it also more formally. So suppose we're looking at the average. Okay, so spatial average, right? So the average at a given time of the xi. Okay? So the question is, what is the dynamics of this average? What does it do? Okay? And in what respect is it true or not that it's like a cleaned up version of the individual dynamics? All right? Now, by the time, we're very close to the end of the course, you should know, obviously it's not, right? You're dealing with nonlinear dynamics and so on, what's going to be cleaned up, okay? But we can do it more specifically. Okay? So let's compute m dot. Okay? So let's compute m dot. So m dot is, of course, 1 over n times the sum over I of these f of xi and t. So what's the second term? So it's the sum over I of all these things, right? And so what is that equal to? Well, it's equal to 0, right? Because whenever you have, let's say, x3 minus x4 at the fourth equation, right, you'll also have x4 minus x3 at the third equation. Okay, so it's really plus 0. Okay, plus 1 over n, the sum over I of these individual noise elements. Right? For the moons, it's just completely algebra, right? It's nothing, okay? I've just taken this, and I've computed this sum, right? So it's purely algebra. I'm sorry?
Do you have parentheses around there? Yeah, 1 over n twice.
Oh, yes, you're absolutely right. Yes. Let me put it here, actually. Thank you. Okay. So what can be said about the variance of this term? Right. So all these are independent noise processes, right? Zero mean. So when you take the expectation of the square, right, the expectation of all the cross products are zero, so you just take the sum of the noises, okay? So you end up with the variance of this, okay, so let's call it sigma sub m square is equal to 1 over n times sigma square. Okay? So that's why, you know, you have the typical question, you know, suppose you have a system, let's say in a lab, and you're doing two measurements with two different instruments, and one instrument is of better quality than the other, okay? What do you use for your best estimate? Well, you don't use just the best estimate of the better instrument. You mix them up, but according to how much value you give to each measurement, okay, and that has to do with, you know, how much variance each of these measurements is supposed to have, okay? So here we have measurements which are independent, and they all have the same variance, okay? So when you take the average, you divide the variance by n, okay? And you divide the standard deviation, which is square root of the variance, by square root of n. All right. Now, what can we say about how it relates to this? Well, not very easy to see, right? Because we have the sum of f, and what we would really like is f of m, right? We would like f of the mean, right? After all, if this mean is supposed to be a good estimate of the xi's, right, we would like to have f of the mean. Okay. Well, we can do that by adding and subtracting f of the mean to this equation, right? So we're going to have f of m plus the rest. The rest we're going to optimistically call epsilon, but it's just a number. Okay, it doesn't have to be small. We'll see what it is now. Okay. So this is just this term where added and subtracted f of m. Okay, and so epsilon is basically the difference between f of m and this term. More precisely, between this term and f of m. Okay. Plus 1 over n, sum over I of these noises. So we see that as far as the dynamics of m, the mean, is concerned, the spatial average, right, is concerned, you can write it as f of m because you forced it there, okay, and you have this term epsilon, which is this minus f of m. And then you have this noise, which is averaged out noise. Okay, so this noise term, of course, this noise term is definitely better than the individual noise, okay? Because of this relation. Okay, its variance is 1 over n, what it was used to be. Now, as I said, you can develop tools for stochastic contraction, at least in some basic, do some basic computation on stochastic properties of contracting systems. And so it can be shown, I will just say it here, that this term here, of course, this minus f of m really depends on what these systems do, and the systems depend on the noise. What the systems do depend on the noise, so this term is itself a stochastic term, okay? So it's kind of a disturbance term, but what you can say about it is in terms of expectation, okay? Everybody understands this, right? This is a stochastic system. This is a nonlinear system driven by noise, and you have n of those, right? And so what defines the mean, this term, which is the difference between this and f of m, is going to be stochastic. So what you can show is that the expectation of this term in absolute value is less than the product of two things, okay? So the first one is sigma squared, not very surprisingly. So in a sense, this term, which is kind of a disturbance term, okay, is going to increase with the level of the noise, okay? So that's not very surprising. Now, the second part is more interesting in some sense. You have d square x over dx squared in absolute value max. Okay, so f is a function of x and t, right? So this is the maximum curvature of this function. Okay? So this function could be whatever, depends on x and time. And this is the maximum curvature, the second derivative of this function. Now, what is that a measure of? Not the measure of, but a measure of. The curvature of f. Well, it's a measure of how nonlinear is this dynamics, right? If f was linear, what would be the curvature of f? 0, right? So if f was linear, this term would be 0. So this is the second derivative. It's a measure, right? Not the measure. The measure is f, right? It's a measure of how nonlinear f is. Okay? And then you have this extra term, which is also interesting. So let me write it as kappa, perhaps, of k times n. So we can show this. I'm just stating the result. Okay. So kappa of k times n tends to 0 as 1 over kn. Asymptotically. Okay. So in other words, this term tends to 0 as kn tends to infinity. Okay. So we can say more precisely as 1 over kn, okay? But the main thing is it tends to 0 as kn tends to infinity. So what does it say? Well, first of all, and not surprisingly, right, if we had linear systems, then this term would be 0, and therefore this whole bound would be 0. And so epsilon would be 0. This, of course, is not surprising, right? If you take the average of linear dynamics, you find the same dynamics. Right? So if this term was linear, you would get 0. And of course, we don't need all of this to show this, right? If you just have a linear system and you take the average, you still get the same dynamics. Okay. So now you have this term, which increases with 3 things. Well, which depends on 3 things. One is the level of the noise. It increases with the level of noise. 2, it increases with the how nonlinear a system is. Okay, so it's a kind of a distortion term, a disturbance term, right? With respect to m dot equal f of m. Right? So it increases with how nonlinear the system is. Okay, and the last part, it tends to 0 as kn increases. Okay. So remember, when we talked about quorum sensing, okay, we said, well, we have this dynamics, okay, and we compute its Jacobian, and when kn is large enough, they will all synchronize. Okay. Now, here, this is saying something else. It's saying, suppose now you add to these same systems noise. Then when kn is large enough, they won't exactly synchronize because of the noise. However, this term which measures the distortion between the dynamics of the mean, m dot equal f of m plus average noise, and the individual dynamics, this term will tend to 0 as kn increases. So in other words, either as you increase the coupling, or you increase the number of terms. Okay? So this means two things, okay? The first one being very easy to check in simulations. Well, both being very easy to check in simulations, and if you have time, I invite you to do that, for instance, on van der Poels or Fitsunagumo oscillators that you already have from your homework. So the first thing says, if you had a linear system, then of course the dynamics of the average would be the average dynamics without the epsilon term plus the average of the noise, okay? And therefore it would be true that when you just look at a patch, you know, you can just look at the region and you take a spatial average over that region, then you're averaging out the noise. Okay. However, in general, of course, it's not true because this epsilon term, okay? And actually this epsilon term is going to increase as you have larger noise, of course, and the system is more nonlinear. However, there is a way to recover the noise averaging properties of linear system in completely nonlinear system, and that way is to synchronize the nonlinear systems, right? Because if you synchronize the nonlinear system without noise, right, then when you add noise, you have this effect. All right? So maybe it's clearer if I try to do a little drawing, although well, hopefully it will be. So suppose you take, let's say, a van der Poel oscillator, okay? And you look at a plot of let's say, the first variable, so it might look a little, not quite a sinusoid, but it might look something like this. So this is, let's say, a V1, or let's say X of a van der Poel. This is just a conceptual drawing, but you can very easily reproduce that. You can very easily reproduce that in a simulation. So two things are going to happen. If you plot the mean of this, okay, with k equals 0, okay, so without synchronization. All right? So you take these. If you plot the mean of these systems, with k equals 0, suppose you add noise, okay, a lot of noise to these systems, so this is going to be all over the place, okay? It's not going to look at all like the original one, okay, with large noise, okay? And each of them is going to have a lot of noise. However, if you plot the mean, it's going to, I'm doing something reasonably random here, it's going to look reasonably clean. Okay? So in other words, you take these noisy things, okay, and you take a lot of them and you take the mean, the signal is going to look reasonably clean. But it will have very little to do with what you're trying to do, which is to average out the noise. In other words, your signal will look clean and reassuring, but it will have nothing to do with what you hope to get, which is to clean up the noise. Okay? So in other words, the question is, what are you measuring when you do these ensemble measurements, these spatial means? What are you assuming you're measuring? Okay? And this simple experiment I encourage you to do, you know, you have all the simulations, so you can very easily add noise, right? You'll take the mean, it's one line of code, right? You'll see it's very clean. But of course, it has nothing to do with the original white line because this is a nonlinear system. Now, however, suppose you do synchronize them, okay? So let me, this is just a conceptual drawing, okay? With Kn large enough, okay, then actually the mean with the noise is going to look like this. Okay? So in other words, it's more or less going to be the original white line plus a little bit of noise. Okay. So what it says is that in the absence of synchronization, because the system is nonlinear, when you take the mean, you get something that looks clean because you're averaging lots of random stuff, but it has very little to do with what you're looking for, which is the clean dynamics. However, the noise averaging property of linear systems can be recovered in completely nonlinear systems if you introduce synchronization between these systems. Right? Synchronization between these systems is a way to recover the noise averaging properties of individual systems. And in very computable ways. You know, you can say exactly how this will depend on noise and on the function, the nonlinearity itself, and on n and on k. Right? And in a sense, it makes sense, right? If there's even a physical analogy to it, right? You could think of these elements as particles, right? And the synchronization is a little like springs and dampers between them, right? So in a sense, if the whole system of these, you know, it could be a model of an almost rigid body, right, with large Kn, right? If this is bombarded with noise, they act together as a team, right, to average out the noise, okay? Although the springs and the dampers could be completely nonlinear. Okay? So in a sense, this says, you know, team behavior gets rid of the noise, right, gets rid of the disturbance, even in completely nonlinear systems. Okay? And incidentally, so you're still driving each of these systems with noise, but you could plot what this was, you know, without any coupling. If you add coupling, the same x1, and of course it would be true for all the others, is going to look very much like its noise-free self, okay? So in other words, each of these individual x1s, so this was the result of driving the system with noise, you know, when you don't couple them. This is the output, right? This is the same output when you do couple them. Each of the individual x1s is going to be protected from its noise by the fact it's teaming up with all the others and they have independent noise. Right? So individually, each system will be protected from this team behavior. And of course, the mean, you can also see the other way, you know, because each system is protected, when you take the mean, it looks pretty much like the original thing. Okay? Right. So that's the basic story, if you want. And it says two things. One is when you're taking a dynamic system and you're taking a spatial average in the presence of noise, are you or not assuming that there's some synchronization process? If you're not, and the underlying systems are nonlinear in non-trivial ways, then it's very likely that your signal is going to look very clean, but it won't be at all what you're looking for. Conversely, suppose that, as in the brain, for instance, you measure these spatial averages and you know they are meaningful because they correlate to behavior, they correlate to other things which are meaningful, then it's very likely that indeed there are synchronization mechanisms, you know, which are going to protect them from this noise, okay, or some version of that. Okay, questions? questions about this? Good. So next time we'll just, which will the last lecture, which will probably be a little shorter, we'll talk about a few extra points. Okay, one of them will be the one we alluded to, which is a technical, it's a technical result, but still useful conceptually. The one we alluded to when we talked about feedback linearization. Okay. And we said when you do feedback linearization, you have these two conditions. One is the controllability condition, which is perfectly natural. It's perfectly natural that you have a condition like that appearing. Okay? And then you have this involutivity condition. Okay? And the involutivity condition was there for a purpose, which was to make this equation that gave us the gradient of Z1, okay, the gradient of the variable we keep differentiating, to make this a gradient indeed, okay, to make this equation integrable, right? So remember we had these G, ADF G, and so on, ADF G, and so on, ADF n minus 1 G, and then we had dZ1 over the x, and that had to be equal to 0, 0, 1. This matrix was invertible because of controllability. Therefore, this gave us this. But of course, for this to make any sense, this better be a gradient. Okay? And we said that led to the involutivity condition, these which were integrability conditions. Okay? Now, as you can guess, and as we'll make just a little more explicit next time, we won't go through all the calculations. Okay? This is a problem you won't have if instead of trying to make the system linear, which might be a little of an overkill, take this saying that most controllable nonlinear systems are really linear systems in disguise. That's not true. That shows this. This shows this very precisely. But in a sense, it was, it was really extremely optimistic to think that was the case, right? So, but what we will show, at least we will state without getting into all the details, is that if instead of transforming the nonlinear system through feedback, so to a linear stable system, you just want to transform it to a contracting system, which is still a nonlinear system, but it has all of these good stability properties and all of these good things we've seen, right? So if you don't try to force the system to be feedback transformable to a linear system, but simply feedback transformable to a contracting system, then in a sense you can do this based on controllability alone. Okay, so that's kind of a technical result, but it makes sense conceptually because, again, we said we started in contraction with just a condition on x, and then we did a coordinate change, and we said, wait a minute, all what we did with coordinate change didn't require z to exist. So we might as well call delta z equal theta delta x without wondering about whether z exists. Okay, so that's exactly the same thing that's going to happen here. Okay, and so that's what we'll see briefly next time.